Assalamualaikum warahmatullahi wabarakatuh and very good morning. So we are going to continue for chapter 4. Okay, next we are going to go to the slide convolution and Fourier transform. So if you remember in chapter 2, you actually learn about the linear time invariant system. So it means that in that chapter 2, you have learned about convolution sum and convolution integral. Okay, convolution integral is for the continuous time signal, and for the convolution sum is for the discrete time signal. So now let's look about the advantages of using Fourier transform when you have to multiply two signals. Okay, so here we are given the input-output relationship, which is a convolution. If you remember in chapter 2, when you're given a signal system HT, so normally when you have a system example motor, okay, HT given by HT, you have an input which is the input might be a voltage, okay, so given by GT, and you want to see what is the speed of the motor rotation, so given by YT. So in order for you to get the relationship between input and output is that you find out what is the equation. So in convolution, you have you actually can do the multiplication by using the convolution integral for the continuous time signal. So YT equivalent to GT, the input, star HT star means that convolution happens here. Okay, so in chapter 4 is that we are, instead of using the convolution integral method, we are going to use Fourier transform method to find the convolution of YT. So we can rewrite this signal in time domain to the frequency domain. So given by Y omega equal to G omega times H omega. So it means that you do the normal multiplication. Okay, and after that, of course, after because you convert from time domain to frequency domain, so normally in the end you would like to get what is the value of the output Y in terms of time domain. So therefore you use the inverse Fourier transform to actually find out, to convert from Y omega to YT again. Okay, so this one F to the power of -1 is the inverse Fourier transform. Okay, so let's look at this just summary. So when you have the time domain signal, okay, you can use the Fourier transform to actually get the signal Y in terms of frequency domain. And after you do the calculation, for example, right now you are doing the calculation for the convolution. So to make it easy, the calculation instead of using the convolution integral, so you use Fourier transform. After getting what is Y omega, then you want to get back what is the Y in terms of time domain, so you use the inverse Fourier transform. Okay, so let's look at an example 7. So using the convolution property to find the Fourier transform of the system Y omega. Okay, so you will need to find what is Y omega for the following input. So you're given the input here. So let's say this one is input XT, so this is not GT but XT. Okay, and the system impulse or the response, the system transfer function given by HT here. Okay, so you are given XT and HT, so they ask you to find what is Y omega. Okay, and after finding Y omega, then go and use the inverse Fourier transform to find what is YT again, right? So in order for you to use the convolution in the Fourier transform, you can refer to the Fourier transform appendix. Okay, so under the Fourier transform property, you will have the pair where you have the pair in terms of exponential. So we look at this example that you have E minus T ut. So we have in the Fourier transform appendix, you have e minus at ut, real value, a is a real value. So, and it must be more than 0. So use that, you can get the Fourier transform is given by 1 over a plus t omega. Okay, and if you look at this example is that the value amplitude is 3 and 2 for xt and ht. So means that 3 and 2 is actually the amplitude a here. Okay, so if you write it again, then you have a, so you have a plus j omega. Okay, so let's look at the Fourier transform property in the appendix. So look at the operation under here. So convolution. Okay, so you have f1t convolve with f2t. So you have Fourier transform is equivalent to f1 omega dot f2 omega. So this is what it means that property. So before the example was the property of the time shifting, time reversal, and so on, linearity. So now we are going to go to the property of the convolution. Okay, so let's do this example, okay, by referring to the appendix just now. So you're given the two equation xt and ht. So xt equivalent to 3e minus t ut. So look at this. Okay, so you have e minus at. So a value is equivalent to 3 here, and a is 1. Okay, if you see here, compare with this equation, so you have a is 1. So write out the equation of the Fourier transform using the pair given. So you have xj omega equivalent to a amplitude, write it out here, a over, so it means that this is actually, we put a over a plus j omega. So a is 3 over small a is 1 plus j omega. So you have found the first equation for xj omega. The second equation ht, okay, is given by 2ea minus 2t ut. So by comparing with this equation, so you find out that a value is equal to 2 and capital A is equal to 2 and small cap is equal to 2 also. So write out what is the value for j omega. So sorry, this one is j omega equivalent to a over a plus j omega. So you have 2 over 2 plus j omega. Okay, now by looking at the convolution property, okay, so the question asks you to find what is yj omega. So yj omega, you can get it by multiplying the input convolved with the system transfer function ht. So you by looking at the convolution property, you will have xj omega times hj omega. So this one, just take out the equation that you have actually solved just now, 3 plus 2j omega and 2 over 2j omega. Okay, this one. Okay, and you will get 6 over 1 plus j omega dot 2 plus j omega. Okay, we are not finished yet. Okay, remember, normally after getting the output in terms of frequency domain, you are going to actually get the output y in terms of time domain. This is the time domain. So meaning that if you look at this equation, you need to do the partial fraction. So you do the partial fraction, so you will have the first value a plus a over 1 plus j omega plus b over 2 plus j omega. So now we are going to find using partial fraction what is a value and b value. So doing the partial fraction, you will get a equal to 6 and b equal to minus 6. So just try it out, take out a piece of paper and try to do the partial fraction. Okay, so you get 6 and minus 6. Okay, substitute the value for a and b into this main equation just now. So you have 6 over 1 plus j omega minus 6 over 2 plus j omega. So you have actually finalized the equation of output y in terms of frequency domain, y j omega. So now is that we are going to get back the output value in terms of time domain. So we are going to use the inverse Fourier transform. So inverse Fourier transform means that we are still going to use the same equation here. Okay, remember this one is from the time domain into the frequency domain. Now we are in the frequency domain, so we are going to inverse it. So we have ft minus 1 inverse Fourier transform. Okay, so by comparing this with this, okay, write out the equation using this formula. Okay, so you can write out yt equivalent to, so what is the a value here? A is 6, so 6 e minus a capital small a is 1, so we have 6e minus t ut minus, okay, second value is you have amplitude 6 also, 6e, you have the small a is 2, so we have e minus 2t ut. So you have the final answer, which is yt. Now let's go to the system characterized by linear constant coefficient with different equation. So for this case is that we are going to have a series of differential equations. So how to do the how to use convolution property for this for the next example. So by using the convolution property here, y omega equal to h omega dot x omega. So we are going to actually use the inverse Fourier transform to get the h in terms of time domain. So which is the response of the system in time domain. Okay. So let's look at this example 8. Consider a stable LTI system, which is the system HT, characterized by the differential equation. So means that if you have a LTI system, then it's characterized by differential equation, means that you have both the input and output. So, and if you see in this example, is that you have the xt, which is the input, and you have yt, which is the output. Okay, so means that they ask you to find what is the system response h omega in terms of frequency domain and ht in terms of time domain. Okay, to do this is that you're going to refer to the appendix. Okay, in Fourier transform appendix, which is you have the differential equation d to the power of n ft over dpn. So you can write it out as j omega n f omega. So let's just look at the appendix. So let's look at the Fourier transform property table. Okay, so if you look at the operation here, we want to look at the differentiation in time. So you have this pair, so d n ft over dt j omega. So you have in the frequency domain is j omega to the power f n f omega. So we are going to use this for the next example. Right, so let's look at the example that we ate. Okay, so we have dyt over dt plus ayt, okay, plus equivalent to xt. So by referring to the Fourier transform differential equation, differential term for the Fourier transform in the appendix. So look at this one, dyt over dt. So this one, if you write it as dyt, okay, over dt, so it means that you have n is equal to 1. Okay, so means that you can write it out as j omega n equal to 1 f omega. So you are using here in terms of y, so this is will be y, and so this one will be y. So therefore, when you write out, okay, the equation is that you have j omega, so j omega of n is 1, y, so you have y j omega. Okay, so this is for the first one, dyt over dt. So next is that plus ayt. So ayt. So ayt you just write out in terms of the Fourier transform. So ay j omega, okay, equivalent to x j omega. Right. So in this example is that you just need to use the Fourier transform pair for the differential equation is for dyt over dt. Okay, so write this out. Okay, rearrange the term, the first term here, then you get y j omega in bracket a plus j omega equal to x j omega. So the question was to find the response time h j omega. So you have h j omega, okay, is equivalent to y j omega over x j omega. So if, let's say if you have this plot diagram just now, okay, you have h here, you have y, okay, you have x. You want to find what is h j omega, so h, or if you write out in terms of y equivalent to h dot x. Therefore, h equivalent to y over x. So that's why you have here h j omega equal to y j omega over x j omega. Okay, so write it out. So just substitute this, so you will get, take this one underneath here, and then this one take it out under here, then you get 1 over a plus j omega for the h j omega for the response time. And from there is to get the inverse Fourier transform. Okay, so inverse Fourier transform for this is that by referring to the Fourier transform table. So for 1 over a j omega, so you have a, capital A is 1, so we have a minus a t ut. Okay, this one is based on the previous example that we did. Okay, so this is the final answer. So let's do this exercise 4. Consider a stable LTI system characterized by the differential equation. So you are given the y per dt squared plus 4 dy over dt plus 3yt equal to dxt over dt plus 2xt for a equal to more than 1. So it means that you add for a value is more than 1. So the question asks you to find the system response in frequency domain h omega t and in time domain ht. Okay, so try to use the differential equation, okay, there, and also using the Fourier transform table. Okay, I give you the final answer here, so try it out. In this exercise you need to do the partial fraction to get the answer for h j omega and ht. Okay, and you have also exercise 5, which is you are given consider the system in example 8. So example 8 is that you find out what is the value for ht, right? ht. So and suppose that you have the input given by xt equal to e minus t ut. So here is that question asks find the output of the system in frequency domain and time domain. It means that you are given ht, okay, from the example 8 there. Okay, and then you have xt. So find what is yt. Okay, means that yt and yj omega. Okay, so that will be the exercise.